Okay. Any questions about anything before we start? We mark down when we're starting, actually. Questions? Questions? Okay. All right. So anyway, what are we doing? We are talking about this important tool called the Endpoint DFT of an endpoint signal X of n. And remember, I warned you that the development here is unlike the development in the book. Please keep that in mind. If you're trying to reconcile what goes on in the lecture with what goes on in the book, we can talk about it on Zoom, whatever. But the bottom line is, the key concept here is an endpoint signal. It's equal to 0 for time less than 0, and it's equal to 0 for time bigger than or equal to n. And so the only important values of it, the only relevant values of it to any analysis are the ones that lie between 0 and n-1 inclusive. So given such a thing, take the Dtft of that, call that x hat of omega hat as usual, and sample it at the cap n equally spaced omega hat values k2 pi over n, and here k is running from 0 through n-1 inclusive, and you get x hat bracket k equal x hat parentheses k2 pi over n, 0 less than or equal to k less than n, and the n numbers you get here, x hat of 0, x hat of 1, up to x hat of n minus 1, that's called the endpoint DFT of the endpoint signal x. And you can write equations that give you the x hats explicitly in terms of the x's without this intermediate step of finding the Dtft of x of n first. One of them I call the D-analysis equation. X hat of k is equal to the sum from n equals 0 to cap n minus 1, x of n, e to the minus j nk 2 pi over n, and that formula holds for the relevant set of k values. And D-synthesis gives you the x's of n in terms of the x hats of k. So this is the sum from k equals 0 to n minus 1, x hat of k, e to the positive, j n k 2 pi over n, and this formula is for n's over the relevant range. And last time I talked about how this is kind of a signal-y view of the endpoint DFT. You take a Dtft and you sample it. This is more of a lineage view of the Dtft, or of the endpoint DFT. It just says you got n numbers, x of n, and you compute n other numbers, the x hats of k. And the fact that we had these two ways of looking at the endpoint DFT gave us a way of approaching our examples. So we did some examples. I want to do one more. And in each case, we had like a method 1 of doing the example. So we did the examples two ways. Method 1 was like this. X of n, find x hat of omega hat, sample it, and you get x hat of k. Method 2, plug x of n into D-analysis and find x hat of k directly that way. So plug x of n into D-analysis, and go from there. None of this intermediate x hat of omega hat finding. Computers, of course, don't do method 1. They do method 2. They have these values, these e to the minus j n k 2 pi over n, or whatever, stored someplace. And so what they do is they just take as the input these n numbers and manipulate them according to the d-analysis equation and give you x hat of k. The computer doesn't even think about the fact that x of n is a signal and that x hat of k is a sampling of its dTFT. It just does that to numbers. And I'm drawing this distinction now because when we move on and talk about the FFT, that's the way we're going to be looking at it. Okay, so one final example. Is x of n is the endpoint signal. It's equal to cosine of n omega 0 hat for n between 0 and n minus 1 and 0 otherwise. That's a perfectly good endpoint signal. Now last time we did x of n is equal to e to the j n omega 0 hat over that time range and 0 otherwise. And what do we discover? We found that x hat of k looks like unless omega 0 hat takes on a really special value, the x hat of k's look like, if you do a stem plot of them, they look sort of like a Dirichlet thing centered on omega 0 hat. Okay, so we found that the x hat of k looked like a quote-unquote sample Dirichlet thing. And here we were ignoring the phase centered on omega 0 hat. And unless omega 0 hat is one of a special value, which is k2 pi over n, then it turns out to be a delta, but whatever. I did that last time. I'm not going to do it again today. And if you apply Euler to the cosine there, you could see that the x hat of k for the cosine example, Euler implies that you can write the cosine of n omega 0 hat as 1/2 of e to the j n omega 0 hat plus 1/2 e to the minus j n omega 0 hat. So you get one of those at half the height. But where are they? Okay, so you find that x hat of k equals, it turns out to be a Dirichlet thing centered on omega 0 hat, and here we're assuming, let's assume omega 0 hat is between 0 and pi. Or actually, let's see, what do I want to do here? Yeah. If omega 0 hat is between 0 and 2 pi, so here omega 0 hat is assumed to be in the interval 0 to 2 pi, as we did last time. We have x hat of k equals 1/2 of a Dirichlet thing centered on omega 0 hat plus 1/2 of a Dirichlet thing centered on what? Well, x hat of k is talking about values of omega 0 hat, or omega hat between 0 and 2 pi. So instead of going to minus omega 0 hat, we go to 2 pi minus omega 0 hat. Okay, so in pictures, let me just draw a picture. If this is our interval of frequency, so this is 2 pi, this is 0, and say, let's divide it. What did we do last time? Was it 8? Was it 12? I think it was 12. So let's see this. 6, 3, 2, Okay, so suppose omega 0 hat is like here, say. This is omega 0 hat. Where's 2 pi minus omega 0 hat? It's here. And what you're going to see for the x hat of k, if you do a stem plot of the x hat of k over each of the k values, you're going to have like a Dirichlet thing whose highest stem is going to be at the k value where that k2 pi over 12 is nearest to omega 0 hat. And then it's going to go down around that after that. And I'm just going to draw this very schematically. I'm just trying to give you a qualitative idea of what's going on here. And there's an imperfection on the board that makes that hard to see, but whatever. So something like this. And out here, you're going to have a similar thing. So and, you know, whatever in here. I don't know. Something like that. So the highest peaks, the highest values of x hat of k, bracket k, are at k values and I don't know what you want to call that k value, if you want to call it k0 or k1. I wrote myself a note last time about what I wanted to call it based on last lecture. Okay. Yeah, K1. Call it K1. Where K1, 2 pi over n, is closest to omega 0 hat, or 2 pi minus omega 0 hat. All right? Now you may say, well, why do we, how does Euler give us something at omega 0 hat and something at 2 pi minus omega 0 hat? Doesn't Euler give us something at omega 0 hat and minus omega 0 hat? Yes, it does, but the 2 pi periodicity of the Dfts means that whatever happens at minus omega 0 hat is also happening at 2 pi minus omega 0 hat. So when we're focusing attention on the interval 0 to 2 pi in omega hat space, as we do when discussing endpoint DFTs, that's where our Dirichlet peaks are going to happen. Okay? So anyway, I did these rather roughly because if you want to do it really carefully, the phases mess everything up and whatever, I just want to give you a basic idea of what's going on with these things. Okay? And in terms of mathematics, again, we have two ways of looking at the endpoint DFT of an endpoint signal. One way is a signal-y kind of way. It's a sample version of the Dtft of the signal. The other way is a Linalge kind of way. It just takes the various values of the signal and linearly combines them in one particular way and gets some other values. And so it's just what you do to a bunch of numbers. All right, so one comment here. Here's a couple of comments. First off, remember that if you have an endpoint signal x of n, so recall that by this process that people in data science and in signal processing call zero padding, we can view any endpoint signal x of n as an m-point signal for any cap m bigger than n. So in other words, I can regard any 7-point signal as a 10 to the 59th point signal if I so desire. Because all it means to be an m-point signal is that you're 0 after time n minus 1 and you're 0 before time 0, and that's certainly true of any n-point signal when n is less than m. Viewing x of n this way as an m-point signal views x of n as a signal that just happens to be 0 over the last m minus n spots. Okay? So you may ask, Okay, if I can regard an n-point signal x of n as an m-point signal for any n bigger than n, what happens if I take the m-point DFT of x of n, viewed that way? So question, what is the m-point DFT of x of n, and related to, in relation to, the n-point DFT of x of n? Okay, so what is it? Well, let's go back to the signally way of looking at DFTs. So using the signal-centric, whatever you want to call it, / method 1 view of the endpoint DFTs. I'm not even going to write the n. What is it? You take x of n, you take its x hat of omega hat. That doesn't change if you regard x of n as an m-point signal. And then you sample it. In one case, you sample it at n equally spaced frequency points, and in the other case, at m of them. Okay. So what do we have? We have x of n. You take x of n, find x hat of omega hat, the Dfts of x of n, and sample it, but at two different quote-unquote frequencies. So the n-point DFT is going to be x hat of k equals x hat of k 2 pi over tap n, 0 less than or equal to k less than n, whereas the m-point DFT of x of n is going to be this, x hat of k 2 pi over m, 0 less than or k less than m. So the upshot here is, if you take an n-point signal, regard it as an m-point signal for m bigger than n, and then take the m-point DFT of that m-point signal, all you're doing is sampling the Dtft of x of n more densely. Okay? So the m-point DFT is a quote-unquote more, or a denser set of samples. How about that? Of the Dtft x hat omega hat than is the endpoint DFT in this case. So that's the relationship between these two. Let me put an is here instead of a colon. Love that. Is a denser set of samples of x hat omega hat than is endpoint DFT. Now, the signal-centric view of DFTs leads one to think, okay, well, what is the DFT? What is the endpoint DFT of an endpoint signal? Well, it's a sample version of the Dtft. So what I'm doing is I'm getting kind of a quick look at what the Dtft of x hat of omega looks like. Okay? And if I want to get a better look at what the Dtft of x hat of omega looks like, I might want to sample it more densely. So by zero padding and taking longer DFTs, I can get a more accurate sort of sampled approximation of the x hat of omega hat. So let me just write that down in some form. So thus, if you view the endpoint DFT as yielding a sort of a rough sketch, so to speak, of x hat of omega hat, the m-point DFT gives you a slightly less rough sketch, a sharper sketch. So the m-point DFT of the same signal gives you a quote-unquote sharper sketch, so to speak. All right. And this will come up a little bit when we talk about the spectrograms later on. And so I want to make sure I get that across. Okay, so that's one thing. Let's see. Another comment about the endpoint DFTs is there's when x is a real valued signal. So that's been our focus throughout. So when x is a real valued signal, the endpoint DFT has a certain symmetry to it. It's a certain conjugate symmetry. And what is that conjugate symmetry? It is x hat of n minus k equals the complex conjugate of x hat of k, when k is between 1 and n minus 1. And it turns out that this conjugate symmetry is useful in applications to digital communications. You may say, well, how? Well, you know, where does digital communications come into this? Let me just mention here, and this is in case you want to go, like in all this, you know, all this quote-unquote free time you have, like out there in the world with nothing to do, you know, as if, all right. If you're wanting to poke around in the digital communications, you know, Wikipedia or literature or whatever, and this is something, if you wanted to take EC 4760, that's a Digicom course where you learn about this stuff, there's a technique called, so this symmetry provides the basis, well, provides part of the basis for the digital communication technique called OFDM. Okay. Now, what that stands for is orthogonal frequency division multiplexing. I'm not even going to write that down. If you look up OFDM on your phone, I'm not going to try it now, but if you do, that'll probably be the first hit. So this is a key technique in digital communications. And I say that this symmetry provides part of the basis for that. The rest of the basis for that comes from a couple of rules, operational rules for the DFT that I want to talk about now that are interesting in their own right. So 3. Like the DTFT, the DFT has with one S, some operational rules associated with it. Okay, so what were the two main operational rules we talked about for the DTFT? Does anyone remember? I know, we're all tired. Come on, somebody. Brandon. Yes, that was one of them, but that's the harder one, so I want to do that second. Okay, but what was the first operational rule we talked about? How about young sir, or Alex? I'll call you Alex because it's so much easier. Yes, the timeshift rule. Okay, we had the timeshift rule for DTFTs. And similarly, we have a timeshift rule for the endpoint DFT of an endpoint signal x of n, but we have to use the endpoint signal style of time shifting, which is what? Yes, cyclic shifting. Okay, so here it is, the cyclic shift rule. Cyclic shift rule goes like this. If you're given an endpoint signal x of n, given an endpoint signal x of n, and some n0 with 0 is less than or equal to n0 less than cap n, comma, the cyclic shift of x of n by n0, call it y of n, has endpoint DFT given by the following. Y hat of k is equal to e to the minus j n0, I'm going to write it n0k 2 pi over n times x hat of k. And that's for all the relevant k values. Right. So if you shift an endpoint signal by a certain amount cyclically, so y of n here, again, this is the formula y of n for y of n itself. Y of n is equal to x of what I call n minus n0 mod n. Okay, so that's the formula for cyclic shift. So there's a simple relationship between the endpoint DFT of a signal and an endpoint DFT of its cyclic shift by some value. And the way you prove this, you can prove it any number of ways. Some people do it by a periodic extension of x of n. I prefer to do it just by plug and chug with equations, with the d and al equation. So it's easy to show using the d analysis equation on y of n. And it's maybe I'll step you through that on the homework. Let me write myself a note. This is good. This is good practice in doing these modular sums and everything. So grab a piece of paper here. Write a note. So let's do cyclic shift rule. The book doesn't do it. That's why you're gonna have to look it up somewhere else. Cyclic shift rule proof using d and l. And it turns out that you end up using the whole thing about e to the j 2 pi over n to the nth is equal to 1. That comes up all the time. Anyway, okay, so that's one rule. Another rule, and this one follows directly from the cyclic shift rule, is the circular convolution rule, right? Or why did I give it away? I was going to ask. Brendan, you guessed convolution rule earlier, and I was going to probe on you and say, well, wait a minute now. We have convolution for normal signals, whatever. Actually, normal is never a good word to use in a math class because there's 3 things normal means. Okay. Anybody ever tell you this? Not to use the word normal in a casual sense when you're talking mathematically? Okay, here's why. Normal either means perpendicular, like when you learn about the unit normal to a surface or to a plane, perpendicular, or unit length, you talk about normalizing vectors, right? And what's the third meaning? What's the third meaning? Jordan. Yes. Normal distribution, Gaussian, right? Bell-shaped curve. So perpendicular, unit length, and Gaussian. So never throw around the word normal when you're in a math discussion. Someone will take you to task. But anyway, Brendan suggested convolution as a rule associated with the DFT, and sure enough, every transform has a convolution rule associated with it. But in the case of a DFT, the only kind of convolution we can talk about in the world of endpoint signals is circular convolution. So, what do we have? In this case, we have the circular convolution rule. And it goes like this. So let me make it look like that. Circular convolution rule says that if you have 2 endpoint signals, so if h of n and x of n are both endpoint signals And y of n is, let me write it on another line, y of n is the endpoint circular convolution of h of n with x of n. And remember, our cool notation for that is a star with a circle and an n below it. So it's their endpoint circular convolution. Then what do you think the endpoint DFT of y of n is going to be? Y hat of k is equal to, let's have a guess. Somebody guess. What do all convolution rules seem to do? Critic. Yes, it's the product. It's just the product. It's h hat of k times x hat of k. And k is always running over this relevant range 0 through n. Through n minus 1, not including n. Okay, so we have these operational rules, and again, you know, this is easy to show building off of the cyclic shift rule, using the analysis equation, the D-analysis equation, and so on. So also easy to show. And so maybe I'll put that one on the homework as well. Haha. Okay, so we have these operational rules. Now, one thing that that makes DFTs so useful in real life is this two-part thing. First off, you can reformulate many computations to be computations doable using just DFTs. That's one thing. Another thing is there exist super fast algorithms for computing DFTs, so-called FFTs. All right? And we're going to dig into the FFT in a minute. But first I want to note that, so it turns out that you can recast a lot of sort of signal type operations as operations involving DFTs and inverse DFTs, computing DFTs and inverse DFTs. And I want to give you one example of that, just one example, because we don't really have time to do a bunch of them. So DFTs and inverse DFTs. Okay, so one crucial example, one key example. And by the way, why is it useful? Like I said, why is it useful to recast signal type operations in terms of DFTs and inverse DFTs? Because we have fast algorithms for doing DFTs and inverse DFTs. So you could take something that was nominally a computationally intensive operation and turn it into a much more efficient one by recasting it in terms of DFTs. Here's one such example. So this is computing ordinary convolutions. Notice I didn't say normal, I said ordinary. Computing ordinary convolutions of finite duration signals. All right. So how does this go? This is kind of fun manipulation. So here's your starting point. Say you have h of n. So I'm going to use the same kind of letters we have over here. Say you have h of n, and it's a p-point signal, capital P-point signal. And by the way, I'm going to assume these are like standard P and L point signals that start at time 0. You know, they could be starting and ending anywhere. All you do is you just shift this whole discussion to 0. But anyway, suppose h of n is a p-point signal, and x of n is an L-point signal. Right? All right. Your goal is to compute what? Well, you want to find their ordinary convolution. So since I'm going to use y for something else in a minute, I'm going to call that q. You want to find q of n equals h of n involved with x of n. And that's just the ordinary combo of the two signals. H of n and x of n. All right, so you want to do that. Now, let's write a formula. First, let's find a formula for q of n, a fairly simple formula for q of n. And to do that, what we're going to remember is something we noted about convolution of finite duration signals earlier in the class. If you take two finite duration signals and you convolve them, what's going to happen to their duration intervals is, in some sense, they're going to add together. So you're going to get a longer signal, a signal that has finite duration, but in general, it's going to be longer finite duration. Now, remember from there's been a lot of recalls in this lecture. There's been the usual opening bell recall, then there's going to be another one I remember, and this is a third one. So we're trying to build on our previous knowledge. That's what happens as we go through this stuff. From our combo discussion, that q of n is going to end up being, in general, is an endpoint signal where, what is n? N is equal to p plus L minus 1. That's how the lengths of the duration intervals add to give you the duration interval q. All right? So that's what you got. You've got q of n as an endpoint signal. And what is a good formula? What is a formula for q of n? We know that, by definition, q of n is equal to the sum from, let's call it k equals minus infinity to infinity of h of k, x of n minus k. And you can rewrite that as the sum from k equals 0 to infinity, because of the h being an endpoint signal. So that, in turn, is equal to the sum from k equals 0 to infinity, h of k, x of n minus k, and that's because h of k is 0 when k is less than 0. And in turn, you can simplify that even further, that this is the sum from k equals 0 to little n of h of k, x of n minus k, because x of n minus k is 0 when k is bigger than n. So here's the bottom line expression for q. Q of n equals what? Well, Q of n is an p plus L minus 1 point signal. It's 0 for n less than 0, and it's 0 for n bigger than or equal to that cap n. So it's 0 when n is less than 0, and when n is bigger than or equal to cap n, which is L plus p minus 1. And for n between those two extreme values, it's equal to this, the sum from k equals 0 to little n, h of k, x of n minus k. And that's when n is between 0 and cap n. Okay, so that's the ordinary convolution of h and x. Now, let's regard both h and x as endpoint signals. Remember, we can do that by zero path, right? We could just think of, even though h is a p-point signal and x is an l-point signal, they're both endpoint signals because p plus l minus 1 is bigger than both p and l. Okay? So, let's regard, as we may, both h and x as cap endpoint signals and compute their endpoint circular convolution. So let y of n be equal to their endpoint circular convolution. So it's h of n cool sign x of n. All right, so let's figure out what y of n is. Right? Y of n is an endpoint signal. So y of n is an endpoint signal. Y of n equals 0 when n equals 0, when n is less than 0, I should say. And when n is bigger than or equal to n. And in between, what is y of n? Y of n is equal to the sum from, let's call it m equals 0, just to distinguish it from here. M equals 0 to cap n minus 1 of h of m x of what? What goes in there for circular convo? Yes. N minus m mod cap n. And that's for these intermediate range of the 1 values. Okay. Now what do we do? What we're going to do is we're going to split that sum using the definition of n minus m cap n. So this is the sum from m equals 0 to n minus 1 of h of m, or sorry, m equals 0 to little n, h of m, x of just plain n minus m, and then the rest of it is going to be the sum from little m equals n plus 1 to cap n minus 1, h of m, x of cap n plus n minus n. Okay? So far, so good. That just uses the definition. When, as soon as m passes n, we have to recast n minus m mod cap n. Instead of it being n minus m, it's n minus m plus a cap n to get in the positive range. All right, now, magically, the second sum is 0. Every term in the second sum is 0. Why? So, no. Every term in the second sum is 0. How come? Well, here's why. The only terms in the second sum that matter are the terms when m is less than or equal to p minus 1. Okay? Because of the h. So the only possible non-zero terms correspond to m less than p, because h is a p-point signal. Okay? For those n values over the range of summation, or for those m values over the range of summation, the argument of x, n plus little n minus m, is going to be bigger than or equal to n plus the smallest possible value, well, n plus n plus n minus p minus 1. And what is cap n? It's p plus l minus 1. So this is going to be n plus l, right? And since little n is bigger than or equal to 0, the argument of x is therefore bigger than or equal to L. So the argument of x is bigger than or equal to L, hence the x term is 0. All right, so you can review this by yourselves, and you can pause it. You can put it on the big screen. You have like a 46-inch TV. Boy, I wonder how these lectures look on that. But the bottom line is, the second sum is 0, which means that we get the following bottom line expression for the endpoint circular convolution of those two guys, regarded as endpoint signals, for y of n. So that is, and conveniently it falls directly below the one we want to compare it to. So here's the bottom line expression for y of n. All right, what is it? It's y of n is equal to 0 when n is less than 0, and when n is bigger than or equal to cap n, which is p plus l minus 1. And in between, it's the sum from m equals 0 to little n of h of m, x of n minus m. That's right. So compare those two. They are exactly the same. The only difference is the dummy variable. I never really liked that expression, dummy variable. I always thought it was kind of, pernicious, pejorative. Who wants to be called a dummy variable? And why do people always pick certain letters for dummy variables? Anyway, same expression. Y of n and q of n are the same. Y of n, the endpoint circular convolution of these two finite duration signals regarded as cap endpoint signals, is exactly the same signal as q of n, the ordinary convolution of those two signals. What does that mean? How does that help? So how does this help? So why is this useful? Why is this a cool thing to know? Well, you can find the circular convolution, y of n, using DFTs and simple math. Doing that, given that we have an efficient way of doing DFTs and simple math, means we have an efficient way with simple math of finding ordinary convolutions of finite duration signals. The basic idea is you can find y of n using DFTs and simple math as follows. Okay, first off, you regard h of n and x of n as cap endpoint signals, where, as usual here, as before, n equals L plus B minus 1. So regard x of n and h of n. Let me write it as h and x, because that's the way I usually talk, just for consistency, as endpoint signals, where n is equal to L plus P minus 1. And compute their endpoint DFTs. H hat of k and x hat of k. 0 less than k less than cap n. Second, take their product, k by k. So set y hat of k equal h hat of k, x hat of k. Now take the inverse endpoint DFT of y hat of k, and you get a signal y of n. And what is that signal y of n? Y of n is going to be the endpoint circular convolution of h and x viewed as endpoint signals by the circular convolution rule for DFTs. Now you've got y, but what is y? Y is just q. Boom, you've computed the ordinary convolution of h and x without doing any convolving at all. You just did a DFT, a simple functional multiplication. That's what I meant by simple math. This middle line here, y of k equals h hat of k, x hat of k. And then you took an inverse DFT. And now you've got the ordinary convolution. So q of n equals y of n, exclamation point. And, oh, I just noticed over here. Anyway, forget that. Okay, so there you go. That's a way of doing convolutions of arbitrary finite duration signals using DFTs. And take my word for it, there's other things, there's other signal processing kind of operations that you can simplify. You can efficiencyify or make more efficient or whatever using DFTs, like, there's block convolution, there's, if you want to learn about more of those, look at a DSP book or take EC3051, whatever. All right. Okay, so I promised you that why this is cool is we have fast algorithms computing DFTs, and that's what I want to turn to next. Okay, but before we do that, are there any questions here? We're going into this in significantly more depth than the book does, but we're also doing it a different way. So again, be warned that that's kind of an issue. So any questions about this for now? Okay. All right, so the usefulness of results like this meaning that one hinges on the existence of fast algorithms for computing endpoint DFTs. Okay, and what are those fast algorithms? It turns out that not only are these around as algorithms, there are special purpose hardware things that do them, like ASICs, application-specific ICs. You've heard of that expression, right? That are built just to do DFTs and using these fast algorithms. And what are the fast algorithms called? These algos are called fast Fourier transforms. FFTs. Everyone says FFT. Again, they don't go around saying fast Fourier transform. People will snicker at you if you talk about, well, let's find the fast Fourier transform of this. They'll go, no, 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 just say FFT. Just say FFT. All right, so algorithms are called fast Fourier transforms, and there are lots of them. But all of them rely on essentially the same kind of mindset, the same kind of thing to do. It's what Peter Dorschuk, my colleague, Professor Dorschuk, likes to call the divide and conquer. Divide and conquer. It's turning the computation into a recursion where you want to compute the big things, so you divide that up into two equivalent smaller things, and each of those you divide up into equivalent or three or whatever equivalent smaller things and so on, and you just recurse on that, and it works out. And so we're going to go through one of these in detail in the class. But let me just, I want to look at where I wrote down when this class ends because I don't want to go past that time. Okay, we're good. All right. So the originators of these algorithms, at least using modern notions of origination, were these two guys, again, at Bell Labs. Alec, we are like, and Eric, Bell Labs, the world's greatest industrial laboratory, when it was around. The originators were these guys, James Cooley and John Tukey at Bell Labs, early 60s, early 1960s. And I say the originators using the modern view of origination. Iconoclastic people will tell you, the iconoclastic people like if you're at a party, say, and you assert that FFTs originated in the early 1960s, the iconoclastic person will say, well, actually the idea goes back to Gauss. And you can roll your eyes, whatever. I always do when someone does that, but I look in the other direction so they can't see me. But anyway, turns out, yeah, Gauss, if you dig hard into Gauss, you find that he actually came up with stuff that looks like this, but I'm going to credit these guys with it. And notice they have first names like James and John. This is before everyone's named Austin and Mason and all those kind of things, But anyway, John Tukey, I want to point out that John Tukey coined a word that you probably use almost every day, okay? And I'm wondering whether you know what that word is. So, John Tukey coined an important word. Every ECE student uses this word at least several times a week, if not every day. Does anyone know what that word is? Huh. So this happened actually in around 1948. Tukey coined the word, okay, no guesses? Okay, how about if I tell you how many letters are in the word? Maybe you'll get it then. Okay, so there's 3 letters in the word. Yes, okay, you got it. You got it. And it's a tie. It's a tie between you 4, so I'm not gonna tell who got it. Coined the word bit. Bit. Which is sort of it's a portmanteau or a contraction or whatever for the pair of words binary digit. And actually I've had 2,200 classes before, although this is only the, fourth time I've taught it. People didn't even know that bit was short for binary digit, much less that Cooley coined it. They just thought that the word existed for all time, but no, it only exists starting in 1948. So anyway, that's a cool thing about Tukey. No pun intended on Cooley's name, but anyway. All right, so the one we're going to discuss. So here, what I want to discuss is what's called. So this is one specific FFT, and the big long official name for it is the decimation in time FFT for computing endpoint DFTs when, it's a long name, eh? N is a power of 2. Okay. So that's what it is. And by the way, if someone came up to, if you had like an ASIC for computing, say, 10 24-point DFTs, right? 2 to the 10th point DFTs, and someone came up to you with a 700-point signal and said, I want to figure out the DFT of this. What would you do? Yeah, Alicia, right. You zero pad it and make it into a 10 24-point signal. Just say, all right, we'll just say it's a 10 24-point signal whose last 10 24 minus 7 whatever values are 0. And we use this ASIC to compute the 10 24-point DFC. But anyway, you can always make, so note, you can always zero pad, say, an L point signal x of n into an endpoint signal. So say n equals 2 to the q point signal if needed. If you want to compute DFT, get a look at spectrum of x whatever, sample it, get a more dense thing. But anyway, that's what you can do to apply this thing, even when the signal you start with isn't something that has power 2 as its number of points. Okay, so anyway, so we assume that n equals 2 to the q for some positive integer q. So anyway, you start with n equals 2 to the q. And usually, when I talk about this, I use L, but we've been using L for durations today, so I don't want to do that. So q is an integer. And x of n is an endpoint signal. And we want to compute its endpoint DFT x hat of k. All right. How do we do that? Well, we don't use, remember, we don't use the signally kind of way of thinking of x of n. We use the method 1 kind of thinking. We use the method 2 kind of thinking. We act like a computer. We just plug x of n into equation D analysis. So equations, and it really, if I wanted to be really precise, I wouldn't say equation D analysis, I'd say equations because there's n of them. D analysis says that x hat of k is equal to the sum from n equals 0 to n minus 1, x of n, e to the minus j k, I always forget that n, j n k 2 pi over n. And that's going to be true for all the k values between 0 and n minus 1 inclusive. All right, so we want to find the x hat of k's. Now, to make things tidier as we go through this, I'm going to introduce some notation, and I'm going to rewrite the sum in a slightly different way. So introduce, for convenience, some notation. So introduce some notation to tidy things up. All right. And this is my notation, and I'll tell you what most people use for this. I'm going to let psi sub n equal e to the j 2 pi over n. Okay? That's my notation. Most people call this, and to me it's really ugly, but I'm going to tell you it anyway. Most people use capital W for this, or capital W sub n for that. And to me, what that leads to is some extraordinarily difficult to read and ugly matrices and stuff on the page. So I use psi sub n. All right. Now, a couple things to note about psi sub n. So observe that. First off, if I take psi sub n to the n, what do I get? And actually, you would get this too if you took psi sub n to the n. Come on, guys. What is psi sub n to the n? E to the j 2 pi over n to the n, which is just e to the j 2 pi, which is 1. E to the j 2 pi is always 1. So psi n to the n is 1. Good? We good? Okay. We good, Hermionis? Yeah, we good. All right, here's something even cooler. Well, I wouldn't say it's cooler. That's a value assessment. I won't compute. Anyway, what if I take psi n squared? Psi n squared. What is psi n squared? Well, that's e to the j 2 pi over n squared, which is the same as e to the j. You can write it 4 pi over n if you want, but I'm going to write it this way: e to the j 2 pi divided by n over 2. Let's make that really clear what I'm writing there. E to the j times 2 pi divided by a fraction n over 2. What is that in psi language? Yeah, it's psi n over 2. Psi sub n over 2. Right? If psi n is that, then psi n over 2 is this. It's what I get when I have psi n and I put in an n over 2 everywhere I see an n. Cool? All right. Good. So those are two observations about psi. And let's rewrite the analysis equation, the analysis in terms of psi. So in terms of d-analysis, or in terms of psi, in terms of psi n, d-analysis reads as follows. There's d-analysis x hat of k equals the sum from n equals 0 to cap n minus 1, x of n times e to the minus j n k 2 pi over n. That's just psi sub n to the minus n k. All right? All right, so now, and this by the way, this holds with the usual range of k values. All right, so now comes the key step. And this is something that I'm not going to try to squeeze in today because I've only got a couple minutes left, but let me just say the next step is key. So next comes the crucial, the key step. What I want to do is I'm going to split this sum into even index terms and odd index terms. So we're going to split the sum into two cap n over twofold sums. As follows. And I'm just going to have to leave that for next time. So this is, maybe we should say, this is the end of ECE 2200 Season 2. And you have to wait all summer to see the first episode of Season 3. No, just kidding. Okay, so anyway, I miss you guys. I hope you're doing okay. Honestly, I really do miss you guys. And I can see your faces when I think about it. It's really cool. But yeah, hopefully I'll see you on Zoom sooner than later if I haven't seen you there already. But anyway, that's all for now. And now I have to go through the multi-click process of terminating the video capture. So how do we do that? Let's see. All right. Here we go. Go down here. Do this. Whoops, no, that was a right click. See, a Mac user doesn't think about which side he or she or they are clicking on because Mac users like me have only one way to click when you get right down to it. So I'm going to stop the video, but it doesn't stop until I confirm.